Scientific notations and significant figures. Scientific notations are generally used by scientists to express a very big number or a very small number. Space scientists, they are dealing with very big numbers, and numbers like distances among the galaxies and the planets. Time is also like how much time light takes to reach from this star to that planet. So all these measurements are very big measurements. They are represented by very big numbers. Similarly, microbiologists, the scientists who are dealing with the microwords, their measurements are too small. So I'm giving you one example of a very big measurement. Like for example, 180000000 meter. It's a very big number. It's very difficult to write this number every time. So I can convert this big number into scientific notation. According to the rules, you're going to put decimal after first non-zero digit. First non-zero digit is this one. So I'm going to put a decimal here, 1.8. And then how many decimal actually is here? If no decimal is written, then it means it is in the last. So how many places we have moved the decimal to the left direction? How many places? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number can be written as 1.8 times 10 raised to power 9 meter. This is scientific notation. You can see how such a big number is written very comfortably in scientific notation. In big numbers, when big numbers are written in scientific notation, now this number is very small as compared to the above number. So the exponential of this, the power of the 10 should be a positive number. So for big number, it is 10 raised to power a positive number. Now let's take a very small number, 0.0000398 seconds. Second is the unit here. This is the time. How to represent this number in scientific notation? Again, the same rule. The decimal has to be shifted after first non-zero digit, which is 3 here. So I'll put the decimal after 3. It becomes 3.98 times. Now, how many places you have moved the decimal? To the right side. See, decimal is shifting to the right. You are making a very small number as big number. So 1, 2, 3, 4. So I'm going to take this number as negative because it's a small number. So exponential power should be negative. This is called as scientific notation, representation of very big number or very small number. The rule says you have to put decimal after first non-zero digit. If you are converting a big number into scientific notation, then the power of the 10 will be a positive value like here. If you are converting a very small number into scientific notation, then how many places you have moved the decimal to bring it after first non-zero digit, then that will be a negative exponential, negative power. So ready for some practice? I'm giving you some numbers here, so let's practice it. 6, 0, 2, 2, 0, 0, 0, 0. It's a very big number. Put this number in scientific notation. So according to the rules, where the decimal should move. Now here there is no decimal, so it means it is in the last. So where the decimal will go? It will go after first non-zero digit, which is 6. Here, how many places it has moved? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what's the scientific notation? 6.022 times 10 raised to power 14. It's a big number. That's why this power should be positive, plus 14. Some teachers, they say like this also, when you are moving decimal from right to left, then it's a positive power. But I think it's easy to understand when it's a big number, the power of 10 should be a positive value, and when it's a small number, then it's a negative value. So let's do one more example. 0.0006202. Put this number in scientific notation. So you have to move your decimal after first non-zero digit here. How many places you are moving? To the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it means it's 10 raised to power minus 9 or plus 9? Minus 9 because it's a small number. So minus 9. And this number will become 6.202. Now, as we have seen that you are using exponentials here, so we need to know some simple mathematics related to exponential. Like for example, if I give you a number x raised to power y, then this x is called as base and y is the power. Now we can do different mathematical operations if bases are same. Like if I give you 10 raised to power x multiplied by 10 raised to power y. Here the bases are same. So it will become 10 raised to power x plus y. If I give you 10 raised to power x divided by 10 raised to power y, this becomes 10 raised to power x minus y. If I give you 10 raised to power x raised to power y, then it will become 10 raised to power x multiplied by y. These are simple exponential mathematics. Let's practice it. 10 raised to power 2 multiplied by 10 raised to power minus 2. What's the answer? Answer is 10 raised to power 0. 2 minus 2, 0. And what is 10 raised to power 0? 1. Any number raised to power 0 is 1. 10 raised to power 10 divided by 10 raised to power minus 10. What's the answer? 10 raised to power 10 minus 10. So answer is 10 raised to power 20. Simple exponentials. We need to practice them. 10 raised to power 10 raised to power 10. What's the answer? 10 raised to power 10 and 10 will get multiplied. 100. Then this kind of mathematics is also very important. Like here 2 raised to power k is 8. So what's the value of k? So what you have to do, you know that 8 is 2 times 2 times 2. That is 2 raised to power 3. So what's the value of k? 3. But the base is same. This base 2 and 2, they are same. So k value will be 3. So these are some simple mathematics related to exponential, which is very important. Let's do one more. 10 raised to power x is 100. What's the value of x? So you will write it like this. 10 raised to power x is 10 raised to power 2. That's 100. 100 is 10 raised to power 10 multiplied by 10. So what is x? X is 2. Like this. So these are simple rules for exponentials. Then rounding off, how to do the rounding of the measurements. For example, look at this number. I want to write down this number in scientific notation, but I want to write only up to 3 digits. So first let's convert this into scientific notation. Is it a small number or big number? Check. It's a small number. You're going to move the decimal from here to here, right? That's the rule. That move decimal after first non-zero digit. So it will become 3.456 times. It's a small number, so exponential power will be negative. 1, 2, 3, 4, minus 4. Now I want to put this number only up to 3 digits. So it means I want to drop this 6. The 6. I want to drop it. So when I'm going to drop 6, 6 is more than 5. Then I will add 1 to this 5, the digit which I'm using for rounding off. So 6 will be dropped because it's greater than 1, 5. So in place of the 6, there is 1 added over here. So after round off, the answer is 3.46. Check this number. Let's say I want to round off this number up to 2 digits. So first I'm going to put it in scientific notation. Move your decimal after 3. It's a small number, very small number. So how many places I have moved to the right side? 1, 2, 3, 4. So in scientific notation, it is 3.44 times 10 raised to power minus 4. I want to drop this 4. I want to drop it. So this 4 is less than 5. So no change. You just drop this 4 and the answer will be 3.4 times 10 raised to power minus 4. Now let's see this example. In this example, I want to drop this 99. I want to put this number in 2 digits. But this 99 is greater than 50. So it means you have to add 1 into this number. So when I add 1 here, it will become 10. So the answer is 2.0. That's the answer. Let's check this one. I want to put this number in 2 digits. So it means I want to drop this 46. So when you drop this 46, it is less than 5, less than 50. You are going to say 50 now. So no change. So it will become 1.9. So that's the meaning of the rounding off. Rounding off is very important because when we are going to express our answers in the right significant figures, at that time, this rounding off is needed. And the understanding of the rounding off, whatever digit you are going to drop, If it is more than 5, then add 1 in the rounding off digit. If it is less than 5, no change. If it is 5, then again you have to add 1 in the rounding off digit. Next is the significant figures. When we were doing uncertainty in measurements, at that time I explained you the meaning of significant figures. So we are going to use the same concept here, and we'll write down the measurement of liquid in these three devices. These devices are used to measure the volume of the liquid. Let's say this is the level of the liquid. This one, the pink line, is the level of the liquid. So according to the marking and according to the rules of certain and uncertain digit, what is the value? What is the measurement here? 3 is marked, 4 is marked, but in between 3 and 4, there is no marking. So the certain digit is 3. After that, there is a decimal because it's less than 4. So you're going to say 3.8 or 3.7. Both the numbers, I think, this is the estimated digit. So I can take 3.7. That appears to be more correct. But you can have error here. If somebody is saying 3.8, that is also acceptable. Milliliter is the volume. Now, check here. This is 10. 10.1, this is marked. 10.1, 10.2, 10.3, 4, 5, 6, 7. So it is between 7 and 8. So I can say 10.7. Look at this, is very close to 8. So 7, 8. This is uncertain. It's not marked. I estimated this. Milliliter, that's the volume. Check this one, 20 and 30. It's here, somewhere here in the center. So I can say 25. And which digit is uncertain here? 5. This is uncertain. In 3.7, 0.7 is uncertain. If still not clear, please check first video on the uncertainty. Now, how many significant figures are here? Only 2. How many here? 4. How many here? 2. So significant figures in a measurement tells you the accuracy of the measurement. For example, let's say there is some silver. You know, silver is expensive metal, and the mass of the silver reported by one student is 10 gram. The other student 10.00 gram. The third 10.13042 gram. So these are the 3 different measurements for the same amount of silver. So according to your understanding, which mass is more accurate? The one with more significant figures. This one. This is more accurate because there are more digits. Only this digit is uncertain. Here, this digit is uncertain. Rest all are certain. Correct. Marked on the scale. So this is very precise scale. So this is the one which is with highest significant figures and has very high accuracy. That's the meaning of the significant figures. But when we are using significant figures, we have to use some rules. So according to the rules are very simple, but you have to keep practicing them. In AP examination, They are very particular about significant figures in free response question papers. They will ask you to put answers in correct significant figures. So first rule says that non-zero integers means any number which is not zero is significant. Like for example, if I give you 23, how many significant figures here? 2. If I give you 1891, how many significant figures here? 4. So all non-zero digits are counted as significant figures. Rule number 1. Rule number 2 is related with zeros. There are different types of zeros. So I'm going to tell you the meaning of the different types of zeros, and then we are going to discuss which one is counted and which one is not counted. Okay, I'm giving you a number here. Understand this number 0.0009000300. Okay, I'll be using different colors to show you different types of zeros. The zeros which are placed in front, these zeros. Can you see there is no non-zero digit in these zeros? These are called as leading zeros. Leading zeros, and they are never counted. They are never counted as significant figures. Okay, now let's see the second type of zeros. This one. These zeros are between non-zero digits. These are called as captive zeros. Captive. And they are counted. They are always counted. Now, let's say these zeros in the end, they are called as trailing zeros. Trailing. But trailing zeros have two scenarios, which I'm going to discuss here. Leading zeros never counted. Very clear. Captive zeros always counted. Always. Very clear. Trailing zeros, two scenarios. One, they are counted if there is a decimal. Like in this number, do we have a decimal? Yes, there is a decimal here. You can see this decimal. So your trailing zeros are counted here. So can you tell me how many significant figures are here in this number? Trailing zeros are counted here because there is a decimal. Leading zeros not counted, don't count. 9 is a non-zero, counted. So 1, 2, 3, 4, 5, 6. 6 significant figures. Captive zeros always counted. Trailing zeros counted because there is a decimal. Non-zeros, rule number 1, counted. So there are 6 significant figures. But if I give you a number like this, 9000300, do we have any decimal here? There is no decimal. So these trailing zeros are not counted. See here, trailing zeros are not counted if there is no decimal in the number. So they are not counted. Captive zeros are always counted. So they are counted. These two. So can you tell me how many sig figs are here? 1, 2, 3, 4. Do not count these trailing zeros because there is no decimal. So there are only 4 significant figures. To understand this rule number 1 and 2, let's do some simple examples. 0.001. How many sigfig in this number? Leading zeros? Never counted. So how many sigfig? Only one. 100. No decimal. How many sigfig? These are trailing zeros. Do I have any decimal here? No decimal. So if there is no decimal, then they are not counted. So don't count these trailing zeros. So how many sigfig? Only one. 101. How many sigfig here? This is captive zeros. Captive zeros are always counted. So how many sigfig here? 3. 1, 2, 3. So these rules we have to practice and we have to use these rules starting from unit 1. We have to put our answer in the correct significant figures. Okay, the last rule is exact numbers. You know that we were talking about significant figures based on the type of the measuring device and how many divisions are there, how accurately is telling you the measurement. But let's take a number which is not measured and is counted, like 10 apples. It's not a measured number, it's a counted number. When you take counted number, then in counted number, we don't have any error because we are not using any measuring device. It's a counted number. If it is 10, it's 10. It's not 9.8 or 10.2. It's not like that. So all the counted numbers, they are called as exact numbers. And we assume that there is no error. So they have unlimited number of significant figures, counted numbers. Another example of exact numbers are defined numbers, the numbers which are the part of the definition. Like for example, we all know that degree Celsius, you're going to learn this in units. Degree Celsius is 5/9 degree Fahrenheit minus 32. You know, this is a defined conversion of degree Celsius to degree Fahrenheit, defined. So here these 5/9 or 32, what are they? They are the part of the definition. They're the part of the conversion. So they are exact numbers. And they have unlimited number of significant figures. Like we know that 1 meter is 10 decimeter. This is by definition. This is a conversion, a defined conversion. So here these are exact numbers with unlimited significant figures. So these are the rules of counting of the significant figures. So now we are going to practice. Okay. Remember trailing zeros, counted if there is a decimal, not counted if there is no decimal. Leading zeros, never counted. Captive zeros, always counted. And non-zeros, always counted. Keep practicing them. Okay, let's see this A part. What are these? These are trailing zeros. So, are they counted? No. So, how many significant figures in this A part, in this number? Only one. Only this one is counted, non-zero. In the B, there is a decimal. So this trailing zero is counted. So how many significant figures? 2. Do not count these exponentials. Okay, when the number is in scientific notation, then this 10 raised to power 2 or 3, they are not the part of your significant figures counting. Only this number will participate. Like here, there is a decimal. You can see the decimal. Trailing zeros counted. So how many significant figures? 1, 2, 3. Here, do we have a decimal? Yes. So these trailing zeros are counted. How many significant figures? 3. In this, what are these zeros? Yes, what are these zeros? Leading zeros. These are leading zeros. Are they counted? No. So, how many significant figures here? Only 2. Leading zeros are never counted. Check this one. What are these? Leading zeros, zeros which are placed in front of the number. Leading zero. Do we have a decimal? Yes. So trailing zero is counted? Yes, this is trailing. So how many significant figures? Don't count leading zero, just count 1, 2, 3. 3 significant figures. In this number, there is a decimal. So trailing zeros counted. So how many sigfig in this? 3. In this number, how many sigfig? 1, 2, 3, 4. These zeros are counted because there is a decimal like this. Okay, now let's see more questions based on it. This book contains more than 1,000 pages. So we are doing counting. But are they telling you the exact number of pages? No. They are saying approximately, slightly more than 1,000. Is there any decimal here in this number? No. What are these zeros? Trailing. So how many significant figures here? 1. Now you can ask this question that if it is a counted number, then why you are taking one significant figures? For counting, there should be unlimited significant figures. But this counting is not exact. This counting is approximate. So whenever we have a counting where we say approximately this much, around this much, then they are not exact numbers. But when they say exactly counted this much, then they become exact numbers with unlimited significant figures. Check this. A mile is about, it's not well defined. So it's not an exact number. And moreover, miles and feet, they are common units. They are not very well defined. How many significant figures in this number? Trailing zeros, not counted because there is no decimal. So how many significant figures? Only 2. These are trailing zeros and there is no decimal. Check this one. A liter is equivalent to this much. This is a quart. So here also, these are not defined units. Defined units are meters, meter cube, decimeter cube. So this quart is not a defined unit. So you have to count all the numbers here. This is captive zero, count it, captive zero. 1, 2, 3, 4, 4, 6, 8. Let's see this one. The population of the United States is approaching to this value, approaching. So it's not exact number. So there is a decimal, there is a trailing zero with decimal counted. And how many sigfig here? Only 2. Check this one. This is a defined conversion, defined. You're going to learn it in the next topic. That's SI units and their conversion. This is a very well defined conversion. So it's an exact number. So how many sigfig here? Infinite or unlimited. These numbers are considered as very accurate with no error. Now we are going to do another question based on it. So I'm giving you practice on plenty of questions because this is one of the important topic and we'll keep practicing it throughout the year. In every question, when we are doing some mathematical question and we have to represent our answer, every time I'll ask you to follow the rules of significant figures and put your answer in the right significant figures. So you're going to do some more rules for sigfig. Okay, check here. The Boeing 747, the speed is around 600 miles per hour. This is the name. This is the name and this is the measurement. So trailing zeros are there. Do I have a decimal here? No. So how many significant figures? Only one. One. This is defined conversion. Centimeter, meter, decimeter, millimeter, micrometer, kilometer, megameter. All these are defined conversion which we are going to do in SI units. So in the defined conversions, defined values, we assume that they are very accurate and the number of significant figures are unlimited or infinite. So here I'm writing unlimited because this is a defined number. 1 meter equals to this much yards. Yard is a common unit. It doesn't come in the SI uh, system or as a defined unit. So here you can calculate the significant figures. How many? 1, 2, 3, 4. It's not an exact number or defined number, right? It's a common unit. So you have to calculate the significant figures. Captive zeros. This is captive. Captive means in between non-zero digits are counted. See this one. Degree Celsius can be converted to degree Fahrenheit by using this equation. And this equation is based on well-defined conditions. So it's a defined equation. So here, these values 9 by 5 or 32, they are exact number. What are they? Exact number. Like you can write this equation like this also. 9 over 5 degrees Celsius plus 32. Just rearrange. I'm just rearranging the equation. Is degree Fahrenheit. So this 9 over 5 and this 32, they are considered as defined numbers or exact numbers with unlimited significant figures. So these numbers are exact. Pi. Pi is used in mathematics. If you are aware of the area of a circle is pi r squared. So this pi is a mathematical number which is actually 22 over 7. But when you put this number in calculator, you will get unlimited decimal places. Unlimited. So this number is it an exact number? No, because it's unlimited, right? After decimal, it's going to be now let's apply all these rules which we have just done on this question You have to represent this number in scientific notation. Exponential notation means scientific notation. So in scientific notation, the number will be 3 point, it's a big number, you can see 85500 times 10 raised to power. You move the decimal from here to here, right? How many places? 1, 2, 3, 4, 5. So 10 raised to power 5. So that's the scientific notation of the number. Now they are asking in this A part, put this number in one significant figures. One significant figure means I have to drop all these numbers. I have to drop all these numbers. But this number is 8 is greater than 5. So when I'm going to drop all these numbers, I'll add 1 in 3. So answer is 4 times 10 raised to power 5. You have dropped this and this 8 is greater than 5. So 3 will become 4. Rounding off. We are doing rounding off. Okay, in the B part, put this number in two significant figures. Two significant figures means I have to drop this complete number, this one. Drop it completely. This is 5500 and this 5 is greater or this is greater than 50, right? You can take it as more than 5. So this will become 3.9. 8 will become 9, rounding off rule, times 10 raised to power 5. So we are placing our number in the number of significant figures they are asking. So what I did first, I converted my number in scientific notation. And then if they're asking one significant figures, I'm going to drop all these numbers. Then using the rules for rounding off, we are writing our answers. Three significant figures. Three significant figures means I have to drop this 500. Now I'll be left with three significant figures. This is 5. So when I'm going to drop 5, I have to add 1 in the rounding of digit. So answer is 3.86 10 raised to power 5. Now it is in three significant figures. Five significant figures. Five significant figure means I have to include 3. This is 1, 2, 3, 4, 5. I have to drop this 0. 0 is less than 5. So no change. Take the rest of the number as such. 3.8550 times 10 raised to power 5. So this is 5 significant figures. You can count the sig fig here. So keep practicing these questions. In the AP exam, generally question will not come like this. Here we are just understanding how to use sig fig. The question will be based on chemistry, some calculations of the chemistry, and then you have to put your answer in the correct significant figures. Now we have to understand two more rules for significant figures. One is when you are doing multiplication and divisions, how to express our final answer. The final answer will always be with minimum significant figures, minimum. Why? Because less significant figures means more error. Like for example, in this particular example here, how many significant figures are in this number? You remember trailing zeros are not counted. So this 0 is not counted. So how many sig fig in this number? 2. How many in this? 1, 2, 3. This 0 is counted, captive. 1, 2, 3, 4. The final answer after doing multiplication, the answer is 8.431 times 10 raised to power 23. But according to multiplication, division, significant figures rule, I have to express my answer in least significant figure of the measurement. That is 2 here. 2 is minimum. Least sig. So it means I have to make this answer in only 2 significant figures, means I have to drop this 31. So you drop 31. 31, 3 is less than 5. No change. Rounding off rule. And it becomes 8.4 times 10 raised to power 23. So you cannot express your answer in more significant figures than any of the measurement used in that particular calculation. Like this one has 2 significant figures. My answer cannot be more than 2. It has to be 2 only. We have to include all errors. Now let's see this number A part. In this case, how many significant figures here? Leading zeros not counted, captive zero counted. So 1, 2, 3. 3 here. How many here? Leading zeros not counted. 1, 2, 3. How many here? 3. How many here? 3. Captive zero counted. So the final answer should be in how many significant figures? The final answer should be in 3 significant figures. So when you multiply all these, I'm sure you will get this answer, 2.26. I'm expressing my answer. Actually, you will get 2.2635, but you have to put your answer only in 3 significant figures. Only in these, so you have to drop this. Use your rounding off rule. So it becomes 2.26. Now, check the C part. So we are doing multiplication here. How many significant figures in this measurement? How many? 2. Trailing zero counted because there is a decimal. How many here? 1, 2, 3, 4. How many here? 1, 2, 3, 4, 5, 6. So your final answer should be in how many significant figures? Only in 2 minimum significant figures. So when you multiply all these numbers, you will get answer as 1.476. You can use your calculator, plug in the values and check your answer. But here, I want my answer only in 2 significant figures. See this 2, this number. So it means I have to drop this 76. The 7 is greater than 5. So it means your rounding of digit will get 1 added in it. So it becomes 1.5 times 10 raised to power 5. Check this one. 2.00. How many significant figures? 3. How many here? 3. So the final answer should have only 3 significant figures. When you do the calculation, you have this kind of number. 10 raised to power 12. Now I have to put this answer in 3 significant figures. So I'm going to drop all these digits. This one, I'm going to drop it. Is greater than 5. This is greater than 5. So my correct answer in correct significant figure is this. Okay, now that was the rule for multiplication division. Now the rules for addition subtraction. So when you are adding or subtracting in your calculations, then the rule for significant figure is different. In that case, you have to express your answer in minimum decimal places. So let me give you one example. Let's say you're adding 1.0 plus 1.00 plus 1.000. You're adding these numbers. Then according to significant figures rule, my answer will be only up to one decimal place because this number has one decimal place. Means the final answer is you just add them. 3 after decimal, you're going to take only one digit. That's the rule. Like for example, if I give you 4 plus 3.0 plus 3.00, what's the answer? This 4 has no decimal place. So my final answer should not have any decimal place. So answer is 10 and no decimal. No decimal because this number has no decimal. So the rule says answer cannot have more digits to the right of the decimal point than any of the original number. Means you have to put your answer up to minimum decimal places of the numbers which you have used for calculation. Is the rule clear? Now this you can take it as AP question, multiple choice question. Here we are going to write down the measurement by looking at the measuring device using that rule of uncertainty, and then we are going to add the volumes using this rule of addition and subtraction for finally deciding the right significant figures. Ready? So what's the volume here? 1 is marked, 2 is marked. So it is 2.2, 2.4, 2.6, 2.8. Now it is between 2.8 and 3. It's below 2.9. Now I have to estimate because this is not marked. So I'm estimating now. So 2.8. After that, I have to take one uncertain digit, estimated one. So 2.85 milliliter. This 5 can be 6, it can be 4. We can have error in this 5. It's uncertain digit. It's not marked here. Check here in this case. This is 0.5, right? 0.5. So it means what is this? 0.1. What is this? 0.2. What is this one? 0.3. So now I'm going to check. 0.2. Now this one is 0.22. 0.24. 0.26. 0.28. So here the measurement is 0.28. But 28 is marked. This is marked. Certain. So I can take one uncertain digit. If you carefully see, it's exactly on the line of 28 here. So I can put 0 here. Milliliter. Now you're mixing these two volumes. You're mixing these two volumes. So what's the final volume? So the total volume will be 2.85 plus 0.280 ml units milliliter. So here, using that rule of decimal points, I have to express my answer up to only 2 decimal places. Because if I add it, I'm getting this as my answer. 3.130 ml. But according to this rule, I should express my answer only up to 2 decimal places, not 3. So I'll remove this 0. That's the answer. This is the rule of addition and subtraction for significant figures. I'm taking you on one question. Let's do this question together. So here we are going to use that rule of uncertainty. Like here, this is the volume. 32 is marked. This is 32. This is 33. So what can be the 32 is marked. So in the A container, I will say it is 32.7, very close to 33. So I'm estimating this 7. This is estimated digit, ml. This is A container. Let's see the B container is here. This is 30 and then 40. In between, there is no marking. So what this can be in the B container? 30 is marked, is accurate, certain. So I can say 32 ml. I'm estimating this to ml. 32 ml here. I'm estimating as 32. You can estimate it as 33. There can be slight error. Estimations are generally, it is the judgment of this person who is observing it. Okay, now let's see the C. In the C container, liquid is here. So it is 32.7. That is certain, 32.7. Now it's very close to 7 only, not to 8. So I can say 32.73. This one, can I take as 7.3? Estimation, you can take 7.4 milliliter, but you have to be slightly accurate with your judgment. You cannot say 32.79. It's not closer to 32.8. So 7.3. So this is how we can label the amount of water with correct significant figures in A, B, C. Now they are saying, what's the total volume? If you add all of them, means I have to add these volumes. So total volume will be and here you have to express your answer in minimum decimal places. Now you can see 32 has no decimal place. So my final answer should not have any decimal place. If I add them like this, I'm getting 98.53 ml. That's the answer which I'm getting. 98.53 ml. But I cannot express my answer like this because according to the rule, addition subtraction rule, I have to express my answer in minimum decimal places means no decimal place in 32. So I have to drop this 53. But 53, this 5 is, this 53 is greater than 50. So I have to add 1 in this 98 and it will become rounding off rule 99 ml. That's the answer. As I was discussing with you about the exact numbers, the numbers in which we assume that significant figures are unlimited, the number is very accurate, all the defined numbers, all conversions, SI conversions, in all those cases, we never consider them during calculation. Like for example, if I'm converting this centimeter into millimeter, I'm using these conversions. Here, I'm not going to use that rule of multiplication, division, and I'm not going to say that, okay, this 1 meter has only one significant figure. My answer should be in one. No. Do not consider, do not consider defined numbers, conversions, or the counted number, which are exact numbers. Do not consider them during calculation. So my answer will be decided by this number. This number has how many significant figures? 3. So answer should have 3 significant figures. Okay, check here. This is by definition. Here 9/5 and 32 are exact numbers. So the significant figures, and this is addition. You can see you are adding 32 addition. So the final answer will be decided by this number only. And this number has 1 after decimal, 1 digit. So my final answer should also have 1 digit after decimal. Addition subtraction rule. We are using addition subtraction rule, right? I'm not going to consider 32 here because it's exact number. I'll decide my decimal places from 39.2. Check here. This is also by definition conversion. And if this is the temperature in degrees Celsius, if I'm adding them together, this 273 is the part of definition. This one. So I'll decide my significant figures in the final answer from the measurement given to me. This is the measurement given to us. Do we have any decimal place here after decimal and any digit, any decimal? No. So final answer will have no decimal. See, this is minus 273. This is plus 273. Answer is 0. You're going to learn these conversions, these scales uh, in the topic where we are going to do SI units, unit of temperature, mass, and volume. There you're going to learn these scales, these definitions. Average numbers. Now I want to take average of these numbers. So when you take average, what are you going to do? You're going to add all these numbers. 6.64 plus 6.68 plus 6.70. How many numbers are there? 3 divided by 3. Now if I use the rule of multiplication and division, this 3 has only one significant figure. Then my answer should be with one significant figure. Like if I do all this mathematics, that answer is 6.6733. If I use the rule of multiplication division, this is division, my answer should be in one significant figure. After rounding off, it will become 7. I have to drop all these. It will become 7. But this answer is wrong. Why? Because 3 is a counted number. 1, 2, 3. There is no error. It's an exact number. So this 3 is not considered in significant figures. It's an exact number with unlimited sec so it is not considered in calculation part. So just ignore it. So it means I have to decide from these numbers, this addition subtraction rule. You're adding these numbers. So I have to use that addition subtraction rule. So in addition subtraction, my answer can have only 2 decimal places. Can you see that all these numbers have only 2 decimal places? So it means I have to drop this 33. When I drop 33, what's the answer left? 6.67. So when we are taking average of the numbers in the denominator, whatever number is there, that number is a counted number and exact number, and it is not this number is not going to be considered in the calculations of these significant figures.